Today we are going to study about device fabrication. So first of all, we all know what discrete circuits are. You might have seen these transistors and capacitors, resistors, and in order to make a discrete circuit, they are all arranged on a breadboard, and discrete circuits are made in 3 dimensions. While an integrated circuit means that all these components, they are on one plane and they are deposited layer by layer. So you might have seen a chip of your phone that is actually an integrated circuit which contains thousands to lakhs to 10 to the power 6 to 10 to the power 7 components per centimeter squared. So integrated circuit means that the entire circuit of active elements, active means transistors, diodes, as well as the passive elements are housed on the same substrate. And substrate is the silicon wafer, which we'll be talking about later. So they are all on one plane. So it is called integrated circuit because it is integration of many components into on one silicon wafer. That is why it is called integrated circuit, and it is also referred to as ICs or chips or microchips. So first IC was made using silicon was made by Robert Noyce, founder of Intel. Before this also it was made on germanium, but with silicon it was made by Robert Noyce. So why silicon is used so prolifically in IC industry, integrated circuit industry? This is because they are abundant. Silicon is abundant in nature. And another advantage is it has a naturally occurring oxide, which is SiO2. And why is SiO2 so important? Because initially when IC fabrication was started, then in MOSFETs the insulating layer was made up of SiO2. But nowadays it is used as a masking material because for lithography. Because at high temperatures, SiO2 acts as a very good masking agent. So we'll understand masking and lithography and all these things later in detail. So you'll get to know a better idea of what we are talking about. So it is seen that the number of components that can be adjusted on a silicon wafer, it increases with time. And if the number of components will increase, that means that the size of the component will decrease. So if the size will decrease, then it will become more and more difficult to arrange more and more devices on a chip. So first of all, let's try to understand what size we are talking about here. So feature size just means that, so here when we are saying that device dimension decrease, it means that the feature size, the entire device will also decrease and the feature size will also decrease. So feature size just means the smallest dimension on the device, which could be fabricated. So in 1960, the smallest dimension was in micrometers, while in 2010 it is in tens of nanometers, while in 2020 it is around a few nanometers. So this was predicted very well by Gordon Moore in 1965, that every 1.5 years to 2 years, the number of chips, the number of components that could be fabricated on a chip will double every 2 years. So the fabrication industry has stuck to the Moore's law, but recently it is seen that some kind of saturation is taking place in the Moore's law, because the number of transistors, the number of components that can be adjusted on a chip cannot go on increasing forever. This is because you see that in a transistor, in a FET, you have a source, drain and a gate. So if there is no voltage applied on the gate, then no current can flow through source and drain. But if there is some potential, then a conducting region is formed and a current can flow between source and drain. So this distance between source and drain is actually what is the limiting size, the feature size that we are talking about. So this size cannot be lower than a few nanometers, because you see that if it is very small, then quantum mechanical tunneling will be there, and control of electrons will be very difficult and almost impossible to control the flow of electrons. And so the switching mechanism will not make any sense if the distance between source and drain is too small. So that is why the saturation of Moore's law is now taking place. While around 30 billion components can be adjusted on 1 centimeter square of a chip nowadays. So let's see how this evolved. Initially, 2 to around 50 components could be adjusted on a chip, and it was called small scale integration. And then 50 to 5000, it was called medium scale integration. While 5000 to 10 to the power 5 is large scale integration, and 10 to 5 to 10 to the power 6 is very large scale integration, and greater than 10 to the power 6 was ultra large scale integration. So now we have actually crossed ultra large scale integration also, because around 10 to the power 7 to 10 to the power 8 components on a chip can be fabricated. So let's try to understand how the chip fabrication has advanced. In 1971, the first chip was made, which was called 4004. It had a frequency of in some kilohertz, 108 kilohertz. Number of transistors on 1 centimeter square were 2300, and the feature size was 10 micrometer. And then in 2000, it was Pentium 5, 1.5 gigahertz of frequency, 10 to the power 7 number of transistors, and 180 nanometer of feature size. And in 2020, the speed of the frequency operation of the device is terahertz, and the number of transistors will be 30 billion, and the feature size is around few nanometers. So you see that if the feature size is few nanometers, then we have some other problems also which we have to take care of. So if the feature size is of the order of 10 micrometer, then a dust particle of 1 micrometer will not be a problem. But if feature size is of the order of few nanometers, then dust particle of the order of 1 micrometer or 0.5 micrometer will destroy the device entirely. Therefore, some controlled environment is required for the fabrication of integrated circuits. So clean room, that is why clean rooms are used. So clean room is actually an environment in which several parameters are controlled, monitored and maintained, which means humidity, temperature, number of particles per feet square, per meter cube, etc. So initially the classification was done based upon the number of 0.5 micrometer particles per feet cube. So if there were 100 particles in 1 foot cube, then it will be called class 100 clean room. If there are 10 particles, it will be a class 10 clean room, and if it is 1 particle, it will be a class 1 clean room. But now the classification has changed, and the new classification is ISO classification, where the one which I'll discuss is ISO 146441. So here we are also not only talking about the number of particles, but about the size of the particles as well. So you see that ISO 1 classroom means that 0.1 micrometer particles will be around 10 in 1 meter cube, and 5 micrometer particles will be almost negligible. 1 micrometer is negligible. 0.5 is also negligible. In 3 meter cube, there will be 1.5 micrometer particle. So ISO 2 is in which 0.1 micrometer particles, 100 particles will be there per meter cube, and 0.2 micrometer will be for 24 particles per meter cube, and so on. So this is the classification that is being used, the latest classification. Okay, so now let's come to the basic steps for device fabrication. So first of all, we require a substrate. So as we discussed, the 95% or more of integrated circuits are based on silicon. So we require a single crystal silicon, a defect-free silicon wafer, on which all the deposition and all the fabrication steps will take place. So in order to make a single crystal, a few techniques are used, for example, Czochralski technique or float zone technique, which we'll be discussing later. And then layering, patterning, doping and heat treatment are the other steps that will be discussed. So single crystal growth does not take place in a clean room, but all the other steps are done in a clean room. So first of all, what is the meaning of layering? So layering means adding some material to the substrate. So addition of material can be done either by growing a material or by deposition of a material. Growing means, suppose we grow oxide or a nitride over silicon. So it means silicon oxide or silicon nitride will be on silicon. So it means that the silicon will be consumed in this process. That is why it is called growth of a layer. But deposition means that the layers are deposited on the surface without consuming the underlying silicon. And various steps that are used for deposition are CVD, PVD, chemical vapor deposition, physical vapor deposition, molecular beam epitaxy, sputtering, etc. So these will be discussing in detail at a later stage. So another step, the next step is lithography or patterning. It is also called patterning. So this is the step actually which will tell you the minimum feature size that could be fabricated with a particular lithographic technique. So if suppose that you are using e-beam lithography, then the feature size could be in nanometers. But if you are using photolithography, it will be in 100 nanometer or in micrometers. So lithography sets the critical dimension of the device is set actually by lithography. So in this, the next step would be doping. So doping means that you add impurities to the silicon wafer or any layer that is deposited. So doping can be done by either diffusion or by implantation of the ions by using a focused ion beam. And diffusion can be done by having a higher dopant concentration around the substrate and heating it so that the diffusion of the ions can take place into the substrate. The next step is heat treatment. Heat treatment is not a separate step. Actually, it will be in doping also, in lithography also. You'll need some kind of heat treatment to be done when we are fabricating the device. So all these steps we'll be discussing in detail in the next few lectures.